Okay, let's welcome last speaker, Professor Meng Xiao-Li, and his topic is artificial Bayesian Monte Carlo integration, a practical resolution to the Bayesian problem. Thank you.
Thank you very much. And I see this conference has a title called The Foundations of Computational Science, but I've seen most of the talks, so tomorrow you'll be seeing them all is on deep learning. There's a lot of learnings, and which is great. But I want to switch topic a little bit. I want you to do some deep thinking instead of deep learning today. And because I want to present to you this problem, which is very easy to present, very easy to describe. And I think that most of you will say, well, that got to be a solution there, but it turned out to be a really hard one. And in fact, that we developed something that eventually I think will be very useful for thinking about how do you do the Monte Carlo integration as a statistical problem. Okay? Most time we do Monte Carlo integration is a very simple-minded way of doing it. Let me just show you what is this. This is right. Okay. So I'm going to present this thing. I'm going to tell you people think it's a likelihood paradox. There is in statistics there's this whole concept called likely function, right? If you haven't studied likely function, then you should study a little bit more statistics. The likely function is incredibly useful, although I understand in the machine learning content, you sort of almost ignore there is a likely function. But I want to just give you the very basic so-called Monte Carlo integration, and I tell you what the problem we're trying to solve, why it turned out to be hard. Typically, we do Monte Carlo simulation, say you have a sample from some density, right, some distribution, and with respect to a measure, often we do not worry about the measure, but for this talk, the measure is incredibly important. Typically, we have Lapika measure, or we have counting measure. These are the very basic. You go back to your measure theory, these are the most basics, right? And the whole idea of Monte Carlo integration is based on so-called the law of large number, right? If you have ID draws, you say take the average of that according to purposely called the frequentist theory, because all you do is say by the law of large number, or maybe you even don't need that as an unbiased estimate of this quantity, right? So the whole idea of Monte Carlo integration is say, I write my integration, something I want to know, and I can't really do it analytically. I write them into a way that it can be sampling from some distribution, then I do a sample. This is pretty much almost all the Monte Carlo simulation. There are a variety of sort of fancier, stratified, and all sorts of things, weighted important. But the basic idea is this frequentist idea. Averaging, you got it right. Okay? So now I'm going to tell you a very simple problem that this theory does not seem to apply, although any statistician would say, oh, there got to be a very simple solution to this. Okay. So suppose I want to do this. Suppose that this function, this I cannot do, but often in situations I may have the following situation. Right? Often I cannot do this, but I found some kind of bound on this guy, right? I have a bound, mathematically some bound. I can say this guy, let's say I can show hx is, let's say, it's big, less than some big hx, but for this guy, it turned out to be very easy to integrate. Let's say this is some upper bound, okay? That, you can imagine our situation, you just replace something by some easier function, you will get an upper bound, right? Okay. If you get the upper bound, then the Monte Carlo method you're going to use, they don't take into account this information. As a statistician, everybody says, well, there's a Bayesian solution, but now we have a real prime. This is the kind of prime that in real life problem you don't get. It's a mathematical bound, so there's no way it can exceed it. It's a truly right prime. So you see, okay, now I want to have this, and often you probably can even get the lower bound, right? So suppose you have this analytical information. How do I use this information when I do Monte Carlo simulation? Because if I do that, my answer should be better. That's one type of problem, okay? This is using mathematical bounds. The other type of problem is, let's say you have now done Monte Carlo simulation, but you have some kind of numerical software. That's some numerical integration. You get any answer. You may or may not like the answer. But numerical integration, particularly for high dimension, it may not be trustworthy. But on the other hand, it gives you a number. And you often in numerical procedures give you some kind of error bounds. So you get the rough sense, say, from a numerical software. Right? You may get something like, the C, there's some kind of interval. It's not exact. This is like a mathematical bound. So this is absolutely correct. But they have some kind of, say, converse interval. Let me use some C star. Okay? So you got that piece of information. That should help you too. The question is a very simple one. How do I utilize this information when I do Monte Carlo simulation? Most statisticians, myself included, first time I saw this problem and said, this could be trivial, right? I can write down a likelihood function. I am the one simulated from this distribution. Therefore, there's no question about what's the correct likelihood, right? The likelihood function is simply write down your probability of how you generate your sample that connects with things you don't know. You write down the likelihood function. Can I erase this?
Yeah.
Okay. I don't want to erase hard enough, so. Okay, so the idea is, the general likelihood theory is very simple, right? Let's say you have let's say your data, let me use a different X, I'm confused here. Suppose you have y1 to yn, let's say it's ID from some distribution given unknown parameter, right? So that's a likelihood. The likelihood function it simply rewrites, it's become a theta given y, it's proportional to fy given theta, right? Because that's a likelihood function. How I do likelihood functions, reverse the role, right? Think about what would be the theta, what's the most likely theta generate the y I have just observed, all right? So now there's a phi, which is a pi theta, right? Okay. For example, if I truly know the things are contained here, I can put the phi, say, it cannot go outside. The support had to live here. The inside may assume uniforms, assume something else, right? Okay, so that's a phi. So the whole Bayes theorem tells you you can get the posterior by multiplying by these two, right? So you get the posterior of theta given whatever the data is. I should be careful at y1 to yn. I have this data, right? And that's the multiplication of I equal 1 to n. This is the whole likelihood because I have ID data multiplied by my pi, right? Okay? And then you got the posterior, you do all the things. And then in fact, what's the most ironic part is, the reason we require so much Monte Carlo is because of the Bayesian computation. The Bayesian computation often is very hard to do, you do Monte Carlo, all right? So now it seems very natural that if I'm using computation to solve Bayesian problem, can we use the Bayesian philosophy itself to solve a computational problem? Why not? Okay? And often in statistics, people debate not about this formula. They debate about where did you get your likelihood? How good is your model? Okay? And where did you get your phi? How good is your phi? Now, frequentists will be mostly worried about this, Bayesian worried about that, and they will debate with each other forever. Okay? Interestingly, in this content, there's no question about the likelihood. I know general data. There's no question about the phi, maybe slightly what's inside, but often these are pretty good products. Right? All right, so I have now give you enough sort of the appetite. Now I'm going to introduce to you, say, well, once you start doing this way, you realize there's something really quite wrong. This actually puzzles a lot of people, a lot of really great people. Okay, so let me first write down what's the likelihood in this particular case, right? If I have data as ID, each had px equal to that, the likelihood, as I just said, is a flip of the data given my h is the quantity I want to know, but each one of them is a probability, right? It's pxi, that's the probability. If you look at the function, there's nothing unknown at all. So the likelihood becomes completely useless if you look at it this way. Following me? I write down what's the probability, how I observed my data, right? And each one of them I tell you that are from something I know. When I write that down, I get very puzzled. You see, the whole idea here is you have to have something connected with what you don't know. What we do not know here is the h, is the integration. But the whole entire p
I certainly know what the H is. I know what the P is because I sample from it. Or at least for professors, at least your students know it. You probably don't know it, but your students know which one they sample from. I hope. So when we start writing a likelihood, it seems like the likelihood function suddenly said, I don't know what to do. Okay, let me make it even more interesting. This is the very basic one, and the next one is essentially very much the same. The next one is this. This is what the people call the normalizing constant paradox. Supposing you have draws from a density which is unnormalized. And many of you know that in order to sample from distribution, you don't really need to know the normalizing constant because sampling only requires the relative frequency. Right? So you can sample from the whole idea of microchip Monte Carlo is saying you can sample without knowing the normalizing constants. But often you want the normalizing constant, but the normalizing constant is easy, right? Because we know the whole distribution had to be integrally equal to 1, so therefore the C had to be determined by this integration, right? So the idea, if I have the draws from it, it seems like I should be able to just do this. Well, let's try to do the likelihood way of doing this. What's going to happen is, well, let me see. Okay, so what is the likelihood? This time it seems that there is a C here. Now, each one of them, the probability of observing each one of them is the QXI divided by C, and it's IID, so the likelihood, the so-called likelihood, if you do that, it's a product of everything, and anytime you do the likelihood function, everybody tells you any quantities known should be ignored, because that's a multiplicative factor. You end up with a likelihood, yes, there's a C there, but this doesn't seem a good likelihood. There's no data now, there's just N, right? If you maximize this, C is 0. Okay? So what went wrong? And this was actually really puzzling. This is actually, you can read, there was a blog written by Larry Wasserman for the statisticians, you know who he is, so he's also a great machine learning person now. So he wrote this whole thing, and he attributed to Ed George, again for statisticians, you know who he is. He's Bayesian, he's at Wharton School. And they basically call this thing, they call it the normalizing constant paradox. Paradox in a sense is, it's a case where everything's known, seems like the likelihood theory should apply very well, and then suddenly everybody look at the function and say, we don't know what to do with it. I can't get anything out of this. Okay? Now, this was written actually 2012, but nobody reads anything because actually this exact same problem puzzled me. I think June, you probably left at Chicago. It puzzled Augie, was June's advisor, one of June's advisors. But Augie, me, and also Peter McCullough, another great statistician at Chicago, when we initially started, we were just like everybody else. We were completely puzzled with what's really going on. All right? It took us a really long while, although long before this. We actually wrote a paper, which I put in the abstract, I think it was 2003, so 10 years before this was discussed in a journal Royal Statistical Society as a discussion paper. We actually figured out what to do. It turned out to be really a very beautiful theory. I'm going to explain to you what's going on and show you why this problem is not trivial and why there's a lot more research can be done. Basically, what we're talking about here is not about sampling Monte Carlo. It's that after you have the sample, how do you best utilize the information to do your Monte Carlo? So basically, analyzing Monte Carlo data as if you were analyzing real data. Okay? So that's the whole. That's what. Is that clear? Have I set up enough puzzle you that there's something puzzle? Okay. So now let me. And in fact, that I think Larry wrote in the textbook about this problem as well. So one of the conclusions was draw a simulate the likelihood method that seems like useless for Monte Carlo, and I completely reject that, right? Because if you think about it, it's quite sort of ironic. When you have a real data problem where you don't know the model for sure, you don't know the price for sure, there's a method that's seemingly powerful. The reason using maximum likelihood estimation or Bayes is because it sort of contains all the information. And then suddenly when you have a problem where a model is not in question, price is not in question, the method becomes useless. That sounds just intellectually is very puzzling, at least. Right? Okay, so we knew there was a solution, but it turned out that you just have to be very careful. Okay, now let me try to convince you what went wrong that in everybody's thinking. including ours at the beginning, but eventually we figured out. So you have to be very careful when you're thinking about information, right? Let's look at this equation, this simple expression, C equal to this, right? So anytime we talk about information, we talk about information all the time, but you have to, when you handle information, you have to be very careful. Okay, let me explain what I mean by that. We assuming this Qx, which is the unnormalized density, we assume it's known. What do we mean by it's known? We say you can evaluate the function at any x you choose. That is what we mean by known, all right? I'm very careful. I'm not talking about I know the function for. I'm talking about you will be able to evaluate, which is good enough these days for the computer. That's what I mean by known. All right, so if you assume that is known, and everybody assumes this mu dx is given, is that either it's a counting measure, live on integers, or it's a Big measure, right? It is known. It's entirely known. It's a mathematical object. If this is known, there's absolutely nothing unknown about the C, right? All you do is just accumulation, right? If it's a finite counting measure, just adding them up. If it's integration, you do the bigger integration, right? So this is a sort of a difference between sort of mathematical thinking and the statistical thinking. In the mathematics, in this case, there's nothing to infer at all. Everything is given. The whole idea of statistical inference say, there's something that's unknown, I can do something about it. So the likelihood theory is telling you that if you set up the problem as if this is known, you don't have an inference problem to start with. Don't blame me that I cannot deliver anything. I should not deliver anything, because there's nothing inferable. Okay? So the way to think about this problem, it took us a really long while. I said, how the hell am I going to handle this problem? How do I turn this into an estimation problem? It's a following. Well, this is known, right? But why we're not doing this calculation? Is it because this guy, its support is too vast, too large. Whether it's countable, uncountable, too large. So all Monte Carlo is doing the following, right? Why Monte Carlo? Monte Carlo said the support is too large to enumerate. If it's uncountable, obviously too large, but even it's countable, it's a combinatorial problem, right? But if it's manageable, who does Monte Carlo just evaluate this, right? So the whole idea of Monte Carlo, we have to think about the following. The Monte Carlo is actually really say, I cannot use this guy. I have to replace this baseline measure by a measure living on finite number of points. So it's an approximation theory. It's approximating a perfectly knowable, you know that the measure by something living on a finite one. And that's the empirical measure. That's what they do Monte Carlo, right? So if you think about that way, you immediately see the problem here is not about estimating the C. It's about estimating the mu. Is that clear? Now that sounds very odd. You say, well, I know mu. Why should I estimate the mu? Well, let's don't use the word estimation. That's got everybody confused. It's an approximation. Approximate something living on infinite or too large by a measure on the finite point. Once you think about it that way, mathematically, it makes no difference whether you call it estimation or you call it approximation. The mathematics follows will be identical. Now you can see what I'm doing. It's going to be non-parametric estimation. Everything follows beautifully. But the key is to recognize this is not the parameter. This is not the likelihood parameter. The likelihood said my parameter is mu. Is that clear? So that's the first step. Once you know the mu, you can estimate anything you want. Just use this. Just replace the theoretical measure by the empirical measure. Everything else follows beautifully. Okay? There's another really important point I'm going to make later, which I'm going to preamble a little bit. By recognizing I am actually replacing this by this, in this straightforward replacement, I'm not using any knowledge about the mu. But I could. I could use some knowledge about the mu. The moment you start using the knowledge about mu, it's like you're setting up the prime. You're setting a prime, but your parameter is no longer single, is no longer a one-dimensional, even multi-dimensional. You're talking about the prime on the entire measure space, which is for people, some of us afraid of that, but if here in the mathematics center, that's completely trivial, right? You're just talking about measures themselves as a point. Okay? But operationally, that's not easy. So I'm going to tell you a little bit more about that. Okay, so now you get the picture. What I'm going to do now is to explicitly recognize this is a part of the mu is part of the parameter. Now I can set the likelihood. Okay, so the parameter is this infinite dimensional measure. Oh, doesn't have the infinite dimension, but it's very. So what we did in that paper back in 2003 is really to set up the parameter, to set up this as a parameter. Now where was a little bit more ambitious. Instead of having one sample from one density, we have like basically have like k different density. You can have simultaneously, you can estimate lots of things. So then you set up this thing. You set up that. Then it's very easy to write down what is the likelihood function. Well, likelihood function is a function of mu. So it's a product, right? Because each one is an ID. There are k of them, so it's another product. Everybody else was writing likelihood without this mu term, then you run into the problem. Okay? But if you write down this mu term, then you see there's not a problem because remember the C itself, the normalizing constant itself, is a function of mu. So there are ties between these two. That's perfectly maximizable. Okay? So if you write down, because they're subject to these constraints. For people who are familiar with the whole theory called empirical likelihood, this pretty much is empirical likelihood. Okay? Because another way of thinking about it is these C's, they're not free. You cannot assume this is known and this is unknown, right? Just as I said, they have connection with each other. So you can set up the likelihood function as the function of the mu, and you can put down, and you can also formally show that the MLE will only will have mass at the MLE for the MLE means maximum likelihood estimate. That if you put the measure has a mass on somewhere you have not observed, that cannot be MLE. It's very easy to show because the data said, if you don't give me anything else, the most likely one is live on what I have seen. Don't tell me what I have not seen because I have no data to support it. Okay, so you can formally maximize this thing. So if I do it, what answer would I would have got? Well, you can set up an equation implicitly for these mu's, but you do realize one thing though. You should realize one thing that I can estimate these measures only to a proportionality because you can simultaneously everybody. So you can see here there's but you can also turn this thing into an equation for the C's. Remember the C connected mu, so you can solve this equation to get your estimate of these normalized constants. Because the C appears on both sides, if I multiply by the same constant, that does not change. So this is the problem is identifiable only up to a normalized constant itself. Okay, so you can estimate the proportionality. So the reason I show this is this turned out to be Wing Wong at it's all Jun's advisor. I only work with Jun's advisor. We wrote the bridge sampling paper. At that time, we did not know this framework, but it turned out that what we proved optimal bridge sampling is actually.
I left the tour.
You left the tour. Otherwise, you will be writing those. But I want to show you what this delivers, right? Everybody knows the same. Or everybody should know. This is called importance sampling. Okay, the idea of importance sampling was derived purely through this expectation, right? The idea is if I draw from a different density, okay, and I can form the ratio because if I do expectation, the denominator cancels, you get that, you can do that, right? But what I just show you is the importance sampling actually is an MLE. It is a non-parametric maximum likelihood estimate if you do not make any additional assumption about the baseline mu. Basically, what this says is if you don't make further assumption about the baseline mu, you cannot beat this. All right? The whole idea of getting all these theory right is, because otherwise it all depends on who's more clever. Right? And that's pretty much going on now with all the deep learning machine learning. Is who's clever. There's no theory saying that is the best way of doing it. But when you get problems like this, there is, at least asymptotically, there's a theory tell you don't try harder because you cannot beat this. Okay? So what I just show you, the importance sampling, if you do not make any assumption, be very careful here. If you do not make any assumption about the baseline mu, this is the best you can do. At least there's no way to dominate this. Okay? But Why not? Why not I'm using some information about the mu? Why did I use the mu? Because I cannot use the entire mu, but I may be able to use some information about the mu. For example, for the Lapega measure, we know it's mirror reflect invariant, right? Lapega measure, like, if you have set here, you take a minus sign, the measure is exactly the same, okay? So for the Lapega measure, you have the following property, which is the mu, right? The mu A is the same as, say, mu minus A, right? Okay? So now, what if I say I want to maximizing the likelihood subject to this constraint? Then you will get a different estimate. It's an estimate that actually very few people have noticed, but I'm going to promote, say, you should use that estimate all the time. There's a trade-off, because that estimate is guaranteed to be better than this, if you have RID data, okay? So, for example, here is the estimate. Here is a new important sample estimate. You can use this estimate, right? The typical one is always just do this part. Now I'm saying, well, adding both numerator denominator with with this, and I'm not assuming anything about the p's or q's are symmetric. They're not. I'm not even assuming they live on. Let's say your x only live on the positive part, and this will be just 0. It's kind of fun. But you can show this one dominates the previous one, always, as long as the draw is IID. Okay? So here's my question. This is the deep thinking part. Why can we do this, right? Because it sounds like a magic now, because I'm still, look, I have not increased my draw. It's still the same amount of draw. Now create an estimator is guaranteed to be better, statistically speaking. Right?
So if the original actual measure is only positive, would that be any strict improvement, or if
it's a great question. I'm going to show you.
Okay.
This is one of those cases. I mean, in statistics, there's this concept called a bias variance trade-off.
Okay.
The idea is if the bias is low, variance high. Bias variance low, bias high. This is the case. The improvement is on both bias and the variance. I'm going to show you why. This is one of the very rare cases, which means the original one was terrible, basically. If you can improve from both. So you're absolutely right, because the traditional important sampling, you have to assume the underlying, the base support is larger. Otherwise, you cannot cover. But look at this one. What this does is effectively to expand your measure on one side, flip it on the other side. Okay? So I think I have this example. Let me just show you. Yeah. Well, let me first say a little bit more. It turns out that all I'm doing here is to choose a group with 2 points, the reflection. Basically, all I did is take the original Monte Carlo estimated important sampling, do something statistically called a raw block gradation by doing conditioning, but you're conditioning on that group orbit. Basically saying anytime you take a 1 point, if you have a group, there's a symmetry, anything on the orbit is as good as any one of them. All right? You can do that average. So you can show that if you have two groups, if one is more refined than the other, you do this raw block gradation, it will guarantee to be better. And this one is simply take the simplest one is reflect according to the mirror. Now, the next one you could do, if D is higher, you just do like, +1, -1 on each coordinate. You can reflect that. That's something you get a 2 to, this sum will be 2 to the D power, right? So the reason I mentioned this is see what we're gaining here, where the free lunch comes from, but there's no free lunch. Look, this one I only have n draws, right? I still only have n draws. But look at originally, this one takes how many function evaluation? It takes n function evaluation of this guy and n function evaluation of this guy, right? There's 2 n function evaluations. But when I do this one now, what do I do? I have double the function evaluation, right? Okay, so you can see, this is actually really interesting. This is saying the gain in Monte Carlo efficiency is not by increasing my original sample, but by using them more cleverly, using them more often, right? And then, so it's really much getting to the quasi-Monte Carlo, those who understand quasi-Monte Carlo, which is design points strategically, right? So this is saying, well, why don't we just design, you get this set of draw. If I can guarantee this still be valid draw because the symmetry of the underlying measure, why not use that? Why not? I just keep using them. I can use it as many times as possible. In fact, I can show you that if the group, if I use this group, if this is the translation invariant group, which is like the entire, then you can easily show this thing will have Monte Carlo error 0. Why? Because it will evaluate so much, it's to the origin integration. Right? So what we realized when we set up this way, we said, holy cow, we found a mathematical way to model the trade-off between Monte Carlo efficiency and the statistical efficiency. Because how do you choose the group depends on how expensive is the function evaluation. If you have a problem where the draws are very expensive, like a lot of stuff like Jung does, lots of draws are very, very expensive. But if the function evaluation is very cheap, keep evaluating. Right? But if the draws are cheap, function evaluation is expensive. Forget this. Just keep drawing more samples. Right? So that is the trade-off. So, but this provides a very concrete way, a mathematical way to. So we don't have to argue each other like who's more clever. Well, it all depends on your choice of the group. Okay. Right, so now, I think this is the question. To answer your question. Oh yeah, this I already said. You can choose his group. You can take invariance. You can pick the whole thing. Already said that. Okay. So this is the one that I want to show that even the original one is biased by doing this thing can bias. So here is an example. Right? Suppose you have a Monte Carlo important sampling situations where your original density was living on the entire line, and your proposal was stupid enough only live on the positive line. If you do the classical Monte Carlo important sampling, you will be ending up doing. If you're doing original one, you cannot even do it because the ratio blows up. But if you're doing this one, it actually do it correctly. Because all it does is whenever it's essentially it's that taking the positive part and moving twice. So this one you can see that because it's the okay. And this is actually better than somebody said I could have done a naive important sampling, something like this, right? I do this doesn't work either. But there's also a big lesson to be learned. Most people don't realize this. This actually has a great consequence on something that machine learners care deeply. It's called a divide and conquer. Okay? The idea is that when you divide and conquer, how do you combine them? You have to be careful. Don't combine ratios. Okay? Don't do the sum of ratios. Do the ratio of the sums. And that's almost always true. In all the theory basically say the ratio sum itself is the kind of raw block combination. And this is a typical case like people do the regressions. Linear regressions, gigantic problems. Divide them into very small things. Down regression on each one of them, right? Get the beta. Then average all these betas. And they found like that's pretty bad. Lots of bias. But don't do that, right? You calculate the numerator, calculate the denominator, average those, take the ratio. If the linear regression, you don't lose anything, right? And that's the whole concept of this kind of thinking about what is the right way of getting the statistician called a sufficient statistic. In this case, so I'm showing you. So now, what it turned out to be, there is a Bayesian paradox. There's no likelihood paradox. There's a Bayesian paradox. There's a real Bayesian paradox. So everything I said so far have not touched this problem yet. I just told you how to set up the likelihood problem. Now I want to set up the Bayes, right? Okay, let's say, Xiao-Li, you got the likelihood. Let's set the Bayes. Well, here you immediately run into the problem. The Bayes, for example, said, I want a bound on, I know a bound on C1, okay? But you see the problem? Because my parameter is not C. It's a C, it's easy to set. My parameter is this entire underlying mu, right? So what I need to do now is I need to find a pry on the mu space such that it obeys this constraint, right? Well, if I know how to solve this problem, I don't need any Monte Carlo. I know how to solve the original problem. Because this is actually more computationally complex than the problem I start with. So this is one that so when although our colleague Peter was so happy because he's never Bayes. He said, yeah, that's why you need the likelihood. You don't need to Bayes, right? But the Bayes basically said, I don't know what to do here. Because you run into an infinite regress problem. In order to solve the computation problem, you create a new Bayes problem, which demands more computation. Yes, you can set up that one itself as a Bayes. It would demand even more, right? You get into this sort of infinite regress, you cannot really solve the problem. So that actually is a real Bayesian paradox. Now, there's nothing wrong with the original Bayes theorem. Original Bayes theorem says nothing about solving its own computational problem. This is just when we try to be creative using a Bayesian method to solve its own computational problem, we run into this sort of a paradox. Okay, this is a real paradox. But it turned out there is an interesting way to solve this thing in a very practical way, which I call artificial Bayes. I'm not trying to be one of the artificial intelligent people, okay? But this is a real artificial Bayes in the sense it's going to use an artificial likelihood, okay? And we're going to approximate the likelihood to do through something called a profile. So okay, so basically the real paradox basically cannot solve its own computational problem, which is all right. So actually the way to do it is for those of some of you may be familiar with the whole concept called a profile likelihood. So what is a profile likelihood? Profile likelihood essentially is likelihood way of marginalize doing the marginalization, right? We know that if you're Bayesian, if you have two parameters, theta 1, theta 2, let's say I say, well, I don't care about theta 2, I only care about theta 1. Easy. Integrate that out, right? The Bayes way of doing things, let's say, well, let me just be more careful. Let's do this as a posterior, right? Suppose I say I only care about theta 1. What do? Well, I just integrate out the theta 2, right? So that's the Bayesian way doing marginalization, right? Okay? If you're a likelihood person, what do? Well, they're always doing it. One way is called the profile likelihood. The profile likelihood said, okay, instead of working with L theta 2y, what I'm going to do is, since theta 1 is of interest, right, I am going to hold the theta 1, maximize over theta 2, right? And so that will give me a function which is, let me put some star there. It will be theta 1 which is there. The solution of theta 2 will depend on where theta 1 is, right? Is that clear? Therefore, this whole thing becomes a function of theta 1 only, right? Because this is theta 1, this is theta 1. So this is called a profile likelihood. Profile is sort of like take the theta 1 a slice, do that. Now, once I have a profile likelihood, and it's not exactly likelihood, but it has properties like likelihood. For example, if you maximize this one, it will recover the NLE for maximizing when it still get that right. Not only that, if you take the second derivative of this function, it will still, at the mode, will be same as the second derivative of this function. Therefore, you keep the Fisher information, all the variance calculation correct, but only to second order. Don't push harder. Goes to the third order, things start falling apart. But for most additions, large data, the two orders are enough. So the profile likelihood is not a real likelihood. It's one of the things called artificial likelihood. It has nothing to do with artificial intelligence. Although these days it's good to use that term. When I was talking about this thing, people thought I was talking about artificial intelligence. But that's a real called artificial likelihood. So the idea here is that if we do that, can we do that? Well, look at it here. Well, what's going to happen here is the mu is the one. The mu is like a nuisance parameter. I don't care about the mu. I care about the C. So this is a little bit different than the usual profile. Usual profile, there are two of them. You try to get rid of this. Now I'm trying to essentially get rid of the whole likelihood only mu. I'm trying to get rid of the entire mu as long as it's subject to the constraint that it's the mu delivered to C. So this actually can maximize. It will give you a function of. It will give you a profile likelihood. But there's something really quite interesting. Once you can solve all this, because this turned out to be solvable analytically. Okay, that's what's interesting. Because the mu only live on this many points, there is actually an analytical solution. Except that the solution that involves involving solving these weights. It's actually involving these weights. The weights is a root of this, but if you look at this thing, all it does is it's trying to balance. It's basically saying if the total number of draws, like n of draws, and how do I find the C? It's balanced, basically saying, essentially very much to this normalizing constant problem itself, essentially that the C, that the function, it's a simple numerical routine. You can actually solve it as long as you get this. But here there's something really interesting happen. Okay? So the profile likelihood can be worked out exactly, other than this is the solution of that equation. Okay? But it's a simple one. So this is the correct profile likelihood following the theory. But in the literature, Xiao-Li Geyer, as June must remember this, Geyer at the time did something called reverse logistics stuff. It itself also has a sort of likelihood looking expression. Whenever we make a comparison, we see the only difference from what he proposed and what we discovered is this weight is replaced by the empirical proportion. NR is how many draw from the R density, N is the total number, right? So if you look at these things, say the only difference is between these two. Why? Well, it turns out that at the MLE, this guy and this guy is equal. Okay? This turned out to be an incredibly interesting problem. What's so interesting? Well, if you look at this expression, for any given C, this is a complete trivial to compute, because all involved is log C and a C here. You require no numerical solution whatsoever. So this is computationally very efficient, especially when doing large Monte Carlo. This one every time requires you solving a routine. Now, it's not that hard, except that when you need to large number of Monte Carlo. Right? Like my student was doing this joint work with my student, he would definitely fail this impact of this. This would delay his thesis for years if we keep running. Right? Okay. So there's a computational advantage of this. And we know that this one delivers the correct MLE just like this. The both function maximize at the same place. What's the difference? If you take the second derivative of this guy, the second derivative of this guy, they're different. Right? You can see the function different. But how much is difference there? Okay, so this was the part, this was actually the major contribution of my student. What he did was to show that this is not that hard to show that this one is wrong in the second derivative calculation, but they're wrong by a factor that is very easy to correct. Therefore, you can still run this sort of wrong MC much faster. In the end, you just correct the variance. It's not entirely legit for small sample, but for Monte Carlo tends to be large. So that's actually going to be a quicker, dirty way of doing the computation trade-off. But that's all based on theory. So that's what I was saying. I'm going to show you. The real reason why this is wrong is, as you know, add this correct C is equals to that, but add the C not equal to that doesn't equal. Okay? Now I'm going to challenge this group. I'm going to even challenge June. June knows this thing so well, but I'm going to challenge not challenge you to pick up your brain. These two, if I do the likelihood, if I use this likelihood, put on any prior I want. You see the beauty of it? Now this is a function of C only, right? So now I can put on any prior I want for C only. I no longer need to put on mu. I can just put a uniform on this. Right? This is sort of much trivial, right? So now here is something I'm going to challenge you all the intuition. If I'm using this as a likelihood plus a pri, using this as a likelihood plus exact pri, and you will get the two posteriors, right? Okay, you know these two posteriors, they will be centered pretty much at the right place because this mode is correct. You know the spread will be different because one is correct, the other is wrong. Okay, the question I have is, which one has the largest spread? Is this one or this one? Meaning, is one is more spread? Which one has? Is the correct one has smaller spread compared to the incorrect one or the other way around?
The correct one should have smaller spread.
Because
it seems you use a little more information. So.
see, that's why June is my colleague now. Because most people will be thinking about this one is going to get small. What's up? Because you're plugging something unknown by something known, right? Usually we know when you're plugging something, it's all plugging something like fixing your underestimating uncertainty, right? You would get intuition the other way around. But Juno is obviously right, because this obviously uses more, more information. But how do you reconcile these two things? Because often we tell students, if you're plugging something, you better, you often your variance gets smaller, right? But this is the case that if I plug in this thing, I actually gets larger. I'm going to show you the picture. I think it's on the next slides. Oh, well, okay. Let me actually. I'm going to just leave that as let you think about what's wrong with the plugin. But I show you the theory. As I said, now you can specify any lambda here is just log c. You should always work on a log scale because it's a relative. There's all kinds of good benefit. So basically, we first had to verify. This is with respect to true posterior profile. This is with Xiao-Li guy's artificial. You first, anytime you use artificial likelihood, you even need to verify whether posterior even is proper density. There's no guarantee. Even if the phi is proper, that's the danger of doing artificial likelihood. There's no guarantee. Okay, but in this case, it's easy to show that as long as the phi is proper, these artificial bases are proper. Then here's turned out to be, in order to do its asymptotic calculation, the only thing you need to pay attention to is the two things. There's a matrix G essentially saying how each one is overlapping with each other. If they don't have overlap, you see the problem. You're not going to get good variance. So this is measured. Remember, I have k densities. How the pairwise measure. This is probably the most important. F here is simply how many draws is from the density you have compared to the rest. And we always assume that there's one density we know it's non-line constants as anchor point. And it's easy. You can always create something like a multivariate normal. You know it. Okay? So then this matrix is essentially the reciprocal of these F, plus one of them is the one you already know. So this matrix is entirely, it's a diagonal matrix. It's entirely computable. Why I emphasize this? It turned out to be, you have the following theory. And this is what was done by my students. If you're doing the Bayesian asymptotics, there are two different kinds of asymptotics. One, the Bayesian asymptotics, which is fixed. The Bayesian asymptotics is what's parameter is the lambda. Okay? What's varying, that data is being fixed. You can see in the Bayesian case that they both center correctly, but the variance, as June predicted, this one is actually larger by this factor, which is just the diagonal matrix. Okay, so this is very easy to correct because this is entirely known from the design. But the frequentist, there's no difference in the frequentist, right? In the frequentist, because these two lambdas are identical. So if the distribution of frequentist, you will see everything works beautifully. But in Dubé, it's the other way around. And now usually when we do those things, this is what you give you trouble, right? Typically people say, who cares about the base or the frequentist? Because asymptotically we get the same answer. Even the distribution have very different meaning, right? Here the lambda is a random variable. Here the lambda prime is a random variable. But when you set up the correct likelihood, these two asymptotics are the same. When you set up these artificial likelihood, you better be careful. The frequentist one obviously is the same because they are identical estimated, the same MLE. But then the Bayesian one gets screwed up because the likelihood function was not correct. But the beauty in this particular case, I don't know how general this is. In this particular case, the correction from here to here is trivial. So you can take advantage to doing a faster computation. In the end, all you need is to do. So let me just show you. This is an entirely toy example, estimating the normal example where one density is known, the other density is these direct constants are entirely known, and we did a complete stupid phi because this is just to illustrate. In Monte Carlo, you should never using uniform phi because you're not learning anything. Why bother? But this is just to show how the thing goes. So we actually look at the Monte Carlo mean square errors. You will see there are means. One is using mode. We also look at the base mode plus mean. There makes no difference except that when you look at the variance, this one is this plus 4. Where the 4 comes from is one of the half. and pretty much like this here. So the theory is just, this is the way that I know my student did correctly, right? Prove the theorem, show me the Monte Carlo simulations, and if this thing two matches, it's not always correct, but it's a much high chance that that is correct. But this is an entirely toy example. This is actually the same example you will see. They pretty much said the same, but the incorrect one spreads. So now, before I show you the last slide, or last two cuts of slide, how are we doing time-wise?
Infinite time.
5 more minutes.
They're local.
Right,
They can leave. You're local.
I have a local advantage. Okay, so here's the way to think about it. Why plugin turned out to be having the large variance? This is actually related to something really quite important, right? Because when you look at the likelihood function, right? What the likelihood function is trying to do, I shouldn't write this bad likelihood function. Right? If you have a likelihood function like this compared to another likelihood function like that, right? These two likelihood function, you know this one has more information because it's higher curvature, right? But when you tie it on this way, very small on this way, is actually more variation on this way. This is the score function essentially, right? Because the Fisher information, those of you still remember, the Fisher information actually is the variance of the score function, right? So it's sort of obvious because you want the likelihood self is to vary a lot in order to distinguish them. Because if the likelihood is flat, then you won't be able to distinguish which is which. So when you plug in that thing, you make the variability here smaller. And that's the wrong plug-in, right? Well, plug-in is never the correct plug-in, but that's your intuition goes the other way around, okay? Because that's what happens with the. So I want to show you in this sort of a little bit more real problem. Okay, so this is a 16-dimension problem that one of the hardest computation problems, kind of interesting, is simply doing multivariate normal tail calculation. And many of you have done that, Give you a high dimensional multivariate normal, I say, I want to probability in some arbitrary region, okay? That's not an easy problem, right? Because it's a truncated normal, but the region is sort of this, so you can get all sorts of problems. So basically this, you have to ask my student, it creates all these cases. So here's what we did. We use a non-informative pry, and we used one based on mathematical bounds. Remember I told you this problem you can have mathematical bounds. And then we also used the one, look at some software, get the answers. Okay? So now basically saying, I'm going to do Monte Carlo using non-informative essentially is like original Monte Carlo. And using this, see how much improvement is there, right? Okay. And whether it's worthwhile doing. So what you do is we look at how the mean estimated, the three different price. This is the average based on this is sample size of 1,000. These are include the sample size. These are standard errors. But the most important thing you want to look at, I know these numbers can be complicated, is we translate everything into an effective sample size. Okay? So the idea is originally you have 1,000. Okay? By using this particular pry, it's equivalent to like using 1,300 joules. So you did not make 1,300 joules, but the pry information gets you another 300 joules. And this is like, if this is, so in this case, the mathematical bound was too wide. So when the sample size increases, it's always like in the mathematical bound doesn't do much. This numerical bound is actually pretty good. So in this case, with 1,000, essentially, you essentially sort of tripled your sample size, Monte Carlo sample size. In this case, when the sample size increases, when the Monte Carlo size increases, that kind of gain become less, right? Because if the Monte Carlo eventually become very accurate, your bounds just become not that useful. But this is a very effective way just to show there is a way to use these informations. And in this case, you may say, well, this is not a big deal. Well, it may not be a big deal, but I show you how to do it. It turned out to be quite complicated. But we find this sort of a profile way of doing it. But for me, the most exciting part is really this whole theory allowing you to start thinking carefully, how do you trade the statistical efficiency versus computational efficiency by designing cleverly what these groups are. When I was working with Peter McCullough, Peter obviously is incredibly clever. He was saying, well, we can even play with, take all the numbers, make them into binary numbers. Then you can play groups on these binary digits. there's lots of mathematical game you can play. Because all it does is to create an orbit, basically saying any draw you have on the entire orbit, they're all legitimate draws. As I can afford the computation, I would do it. And it turned out that somebody else, who was the guy named Steve at Ohio, what they did is they actually discovered this way. They called it something called a transfer function. They were using this technique to deal with the reducible microchain. Okay, sometimes the chain gets stuck aware, but if you know how to transport, it actually relates to the whole theory called optimal transport. You basically can, using this, you can move, you can expand your support. But what's interesting is the whole theory gets correctly set up by really not modeling what we don't know, but rather model what we ignore. Because we know what the baseline is, but we ignore its knowledge. We start using part of the knowledge. And if you use full knowledge, you go back to the computation problem you cannot solve. So I hope I gave you enough to sort of think about. I think there's a reference, yeah. These are the original papers already published. The one I'm finishing these examples with the correction, that sort of the very simple correction is with my student, which should be done soon. Maybe it's on my desk. I need to finish it, hopefully this weekend. Thank you very much.
Okay, thank you, Professor, for the detail. Any questions?
So you mentioned about estimating underlying probability measure, as a measure is unknown, but the prior is very difficult to apply because it's as difficult as the original problem. But are there cases where the prior are indeed easy to apply? For example, if you know the measure is factorizable over like easy model over pairwise interactions.
Sure.
And then you have an empirical measure, from your samples.
Yeah, it's a great question. I don't know the answer. My hunch is there got to be some problems that's possible, right? But regardless, all we're doing is now we basically translate the problem into a non-parametric estimation curve. So you get a measure. So you run into. I mean, there are tricks there, but we're happy with this application. We're just happy with the profile.
That's right.
Once you do the profiling, you completely get rid of the thing. You can profile the surprising part. You can profile the entire infinite dimension analytically, other than this sort of one trick to do the computation. We can even do that with this approximate trick.
So I understand the techniques, but intuitively, what this mu is really estimating. So then we know this is really the big matter. Is it estimating some kind of density ratios or?
No. The muse is actually literally just trying to estimate where should I put the measure, right? So what it does is this. The original, let's say counting measure, right? Original counting measure gives everybody essentially equal.
Right.
But this mu, based on your sample, so it is like important. That's a truly important sampling, right? Because your data is going to tell where the measures matters, and it's going to aggregate all the measures and put it in those places, right? And they say, well, forget all the other ones, not important. So, but I think it's best to think about this as an approximation. Like, where do you put the measure will be best approximate. When I talk about estimation, get everybody confused because it's known. Why are you asking something's known? Oh, I'm approximating something's known, which is But that's why that become adaptive.
For the WR hat in the log technique code, what is the estimated computational complexity?
Now it sounds like a computer scientist. I don't know. It's actually not hard because it's simply solving almost like it's a nonlinear equation. But the problem is that one itself is very fast. That's complicated. But except when you do this Monte Carlos, because you have to evaluate it every time. So that's what accumulates. So its order is really according to Monte Carlo size.
Yes, Xiao-Li, I have a question. So, at the beginning, you mentioned that we want to approximate that mu, the measure, right? So, then you told us that the best approximation should be this important sampling.
If you're not assuming any knowledge.
For that case, the procedure is that we already have all those x this data sampled from the original mu. Then we just based on this data position, then we try to find the weight. Then the weight should be
Yeah. So in that case, I did not create anything new estimate.
Okay.
I'm simply justify the existing important sampling is an MLE.
Okay.
But the most important part, then I realized by introducing a little bit knowledge of mu, I can beat that. And I can beat that infinite many times as I do more and more, but it requires more and more functional evaluations. That's a trick.
Okay.
So you essentially try to approximate the mu by the given sample set.
Correct.
It's independent of your Q.
Great question. Well, yes and no, because the estimation of where these data points are, is related to that Q.
So yeah, that's the second question. Why about Q and mu together, we try to estimate together in some sense?
That is fantastic question. Yes. So now that's another topic. You invite me next time. Okay. So because what my students now, the second paper we're going to work on is we're doing the following. Remember we said that these functions like the Q's are entirely known. Well, what if these Q themselves actually have some real parameter in it? Okay? So now we're trying to estimate it is we're trying to, and you have these normalized constant problems, right? The part we're doing is getting some estimate of this, then trying to do MLE. So what my student and I were doing is, well, let's forget this problem. Let's just say, let's treat this mu and sigma all as parameter, maximize them all together. Right?
Yeah.
Okay, so here the results so far. So what the worry is like, can we still get the MLE? Well, it depends on how you estimate these guys now. Okay? So the theory what we have so far is because you're gonna lose quite a bit if you're not careful. The thing is that if you can estimate the baseline measure using these kind of quasi Monte Carlo type of estimated, which has base higher than usual 1 over n, then we can show that you still recover the original MLE. But if you cannot estimate the baseline with more accuracy, then you're starting losing. Yeah, that's just that because there's no free lunch because now the data needs to estimate both the unknown parameter and the unknown sig. So it starts to use information. So that becomes much more complicated. But it's a great question. Yeah.
Can you please relate what you're doing to quadrature methods
To
integration?
Yeah, that's a very good question. The connection is the following. The quadrature method is essentially finding a different way to set up this baseline to find this approximation. I didn't say this is the best way of doing it, right? I'm just saying if you have the Monte Carlo draws, how I'm going to use it. Yes, in fact, as I just said, when we do this thing, we'll be using. So the difference is that this way is to try to utilize the information about the baseline measure. Quadrature of these methods essentially is utilizing the information of the integrand itself, how smooth it is. You're using different kinds of information. Because you can do much better, right? You know these quasi Monte Carlo errors, it depends on how smooth function is, right? Because it started using the other information. So there's a whole other literature. For example, Percy Diaconis used to work on putting on a stochastic process for the function itself, because according to its smoothness, you can estimate those things. There's another general thing you could do. I think probably the most general thing you could do is to include all of them together. You utilize the information on the function smoothness itself, utilize information on the baseline, and you try to estimate this all together. So there's lots of PhD thesis there.
Okay, thank you, Paul.
Thank you.
So I think that last second, welcome to tomorrow morning.